In this lesson, we're going to break down the rolling without slipping motion in a little bit more detail. And we get a kind of neat result here that we can easily see by understanding what are conditions for rolling without slipping due to the overall motion of the wheel that's observed. So let's go back and just recap what we know so far. Well, when a wheel rolls without slipping, it's rolling, so it has an omega. And of course, V tan equals omega r still holds, right? So we have V tan equals omega r, and the same down here, the V tan. I won't write the omega r, but we have the V tan down here again. So that would be the wheel just spinning. Now, if it's rolling without slipping, we said that is the perfect condition, right? The convergence of the conditions where the center of mass speed is also going to equal omega r. So that is what happens with rolling without slipping. Now, you don't have to have both motions, and that's kind of what we're doing here. We're saying, okay, let's first just consider if the wheel is spinning and not going through its rolling without slipping motion. And here, let's consider if it's just translating, and then we're going to put the two together, and we get that really neat result here. So we have V center of mass and V center of mass without the rolling motion at all. When all of the V's equal each other, we see that at the base of the wheel, look what happens. At the base of the wheel, these two vectors go in opposite directions. So there's our without slipping. So when we observe the motion from the ground, so when we're observing the motion here, we see the combined effect that V center of mass forward from the translation and V tan from the rotation at the base of the wheel gives no slipping. There's no relative motion between the wheel and the ground. And that's exactly what happens when your bicycle rolls along. Well, when we combine the vector addition of the center of mass points, we only have V center of mass, so that's exactly what your bicycle is doing. You're moving ahead with the speed V. But here's kind of the neat result. Look what's happening at the top of the wheel. At the top of the wheel, believe it or not, and it is true whether or not you believe it, the top of the wheel has an instantaneous velocity of twice the velocity of the center of mass of the wheel. So if we were to take a photograph of a wheel rolling along, and I will show this to you in class, we will see that what happens when a photograph is taken, if you're moving around a lot, the picture's blurred because the shutter is open long enough to take multiple images. Unless you have taking a really high-speed photo, but we're considered just like a normal type of portrait type of photograph where the shutter will be open for a little bit longer. And what we will see is that when you take a picture, a still picture of a wheel that's rolling along, what you are going to get is a very in-focus picture of the spokes of the wheel down here, and then a very blurred out picture of the spokes up here, and it gets more and more blurry as you move around from the bottom to the top because of the speed being different. Now, the bottom line for us, if we're asked a multiple choice question, we don't want to have to go through a complicated analysis of vector additions. We want to know that if a wheel is rolling without slipping, that the speed at the base of the wheel where it touches the ground is 0, the center of the wheel is moving with a speed v, and that the top of the wheel is moving with a speed 2v. Now, the last thing I have on this page of notes is the two ways to achieve rolling without slipping so that we don't lose sight of what is going on here. So when we have the gears, like this is the back wheel of our bike that we've talked about, the gears are torquing the wheel. So the gears are causing the angular motion. So that wheel will spin in place without friction. And it is indeed friction causing the wheel to go forward for the back wheel. And it's the axle pushing forward on the wheel that is allowing the front wheel of the bicycle to go forward, or the rolling pin if it's a rolling pin, and then the friction on the ground allows for it to spin. So it's kind of a reversal of the dynamic, but the end result is that they will both roll forward without slipping. So in our next lesson, we're going to look at a numerical example of rolling without slipping, but these first two lessons are really our introductory units and covering a little bit of the basic dynamic of rolling without slipping that we don't want to have to give a whole lot of analysis to when we start one of these problems.